Here's another scenario that you've studied before, a mass moving in vertical circular motion. Previously, you've analyzed this using the tools of dynamics and kinematics, but now I'd like to revisit it from the perspective of work and energy. So our first task will be to find the works done on the mass by the two forces acting on the mass, tension and gravity. So the work done on the mass by tension as the mass moves, and now here's the description of the path it's taking, from the bottom of the circle to the top of the circle. So suppose it's spinning, so mass on a string here spinning counterclockwise in a vertical circle, and it's going to start at the bottom and swing up to the top along that semicircular path. We want the work done on the mass specifically by the force of tension along that arc. So we write the work done by tension is by definition equal to the integral of the force of tension dotted with our infinitesimal displacement vector dr along our semicircular path. This time, instead of expressing the dot product as the sum of the products of the components, I want to use the other definition of a dot product. Let's try this. Let's note that ft.dr can also be written as the magnitude of ft times the magnitude of dr times the cosine of the angle between them. The idea here being that at every point on the path, you would take the magnitude of the tension at that point times a little displacement magnitude at that point times the cosine of the angle between those two vectors at that point, and then add up the results of this product at every single point along that path. But we can quickly see that the tension and the displacement are always going to be perpendicular to each other. Tension points in towards the center and displacement is always tangent to the path. They're always at a right angle. Therefore, the angle theta between them is always 90 degrees. Cosine of 90 is 0, making our integrand 0 at all locations. Therefore, 0 work is done by tension along that path. At all points, tension and displacement are at right angles to each other. Over here at the side, tension points inwards to the left and displacement would be pointing straight up. They're always at a right angle to each other. Therefore, tension is not making the mass speed up or slow down at any time. It's only making the mass turn. It's only providing that centripetal force that turns the mass. And so it is adding no kinetic energy and is removing no kinetic energy. Tension is perpendicular to our displacement at all times along that path. Okay, so no work is being done by tension. Next, the work done on the mass by the force of gravity as it moves along that semicircular arc. That's right, the work done by gravity will be equal to the integral of fg dot dr along that semicircular path. And we'll again use this definition of the dot product to express this as the magnitude of fg times the magnitude of dr times the cosine of the angle between those two vectors. We multiply these things together at every point on the path and add up the results. That's the meaning of this integral. So examine over here. Fg we know is constant in magnitude. So the magnitude here is just mg. That's a simple constant. But the thing that's changing this time is the angle, theta, between the two vectors. I've indicated in red here that down here at the bottom, the angle between them is 90 degrees. Then as the mass swings up, the angle becomes greater than 90. Here the angle is 180 degrees, then it's greater than 180. And by the time it gets to the top, the angle between those two vectors is 270 degrees. as we track that angle continuously increasing along that arc. So the angle here is a function of position. So how can we possibly evaluate this integral? The key turns out to be imagining a thin slice of your circle, a thin slice with an arc subtending, a short arc subtending an infinitesimally small angle, d theta. The length there would be the radius of the circle, r. And then the length of the arc here is the magnitude of dr. That's your little step forward along your circular path. So that's the magnitude of dr, which is this expression right here. And if our angle is very small here, then this thin slice becomes well approximated by a thin triangle. And to the extent that the angle is small, the approximation becomes ever better, and we can say that the infinitesimal arc length dr, based on our fundamental relationship for a circle, is equal to r times d theta. That's arc length equals radius times angle, as long as your angle is measured in radians. So dr equals r d theta. And this we can use to transform our integral here. So rewriting, fg we know is just mg. That's the same at all points. So we can pull out that constant. So equals mg. And dr we're going to replace with r d theta. So the integral of r times cosine theta times d theta. dr got replaced with r d theta. I moved the cosine theta in between the two. And now along our path, r is a constant, so that can be pulled out as well. And theta increases from pi over 2 radians to 3 pi over 2 radians along that arc. What we've done is change the independent variable to theta. So we can now actually state our upper and lower limits because theta varies continuously from pi over 2, its initial value, to 3 pi over 2, its final value. And that's an integral we can evaluate. So pull out the r and we get mgr. Collect those constants out front. And the antiderivative of cosine theta with respect to theta is sine theta. So we're going to evaluate that antiderivative at theta equals pi over 2 and at theta equals 3 pi over 2, the upper and lower limits. Okay, so this will be mgr. Sine of 3 pi over 2 is -1 minus sine of pi over 2, which is 1. So that's -1 minus 1 gives us a -2. So -2 mgr is our result for the work done by gravity along that path, -2 mgr. And the result, which required an evaluation of this trigonometric integral here, the result should be of no surprise. Because although we were clever about evaluating that integral, we could have just used this definition, because after all, the force of gravity is constant along this path. So we could have just used this definition and note that delta x, if we use standard xy axes, delta x was 0, since we started and ended at the same x value. Delta x was 0, delta z was 0, and our delta y was 2r. And our Fy, the y component of the force of gravity, was -mg. So this would have been -mg times the delta y of 2r, -2 mgr. Okay, so in this case, using this expression for our work, I think would have been a little bit quicker. But I wanted to go through it this way to give you a sense of how to transform a work integral into something involving an angle, because that will be handy for us in the future. All right, Negative 2 mgr, that work is negative. That shouldn't be surprising either. Our force of gravity was down, and our displacement overall was at most times upwards, so they were opposing each other. The angle was greater than 90 degrees this whole time, so negative work done by gravity. Follow-up question. And this follow-up question, I hope, will suggest to you why it is worthwhile to calculate the works done by the forces. I mean, we see that this is something we can do now. We can calculate the works, but why is that useful to us? What does that help us find out? It'll help us answer this. To complete the loop, the minimum speed the mass must have at the top of the circle is v top equals the square root of gr. What we mean is that in order for the mass on the string to swing through the top without falling off the path, without the string going slack, is this. This is not something you can prove from energy alone. This requires dynamics. So quick reminder how to prove that. We would look at the top in a free body diagram, gravity and tension, set up Newton's second law in the radial direction, gravity pulling straight down in the negative radial direction, tension also down in the negative radial direction. And the condition is that if we want the string to still be taut, if we want it to not be slack, then we look at the moment when it just barely becomes slack, and that is when our tension goes to 0. Let the tension vanish. That's the string going slack, so the mass is about to fall off the circular path. And if we do that and solve for the speed at which the tension goes to 0, we'll be finding the minimum speed. Okay, so you let the tension vanish. That'll be the minimum speed at the top without falling off the circle. That gives us this. Mass and mass cancel. Finish solving for v here, and we'll get this g times r square rooted, just root gr. That's something you should be able to rederive quickly. So I recommend you both have this result memorized for handy use and be able to run through this dynamics argument to recreate this argument to quickly rederive that result. So that comes from dynamics. Now I want to use the work energy theorem to find the corresponding speed at the bottom. The corresponding speed at the bottom of the circle. Work energy theorem here. What I mean is, if we know the mass has to be going at least that fast at the top in order not to fall off the circle, then that means there must also be some minimum speed at the bottom. It's got to be going at least a certain speed at the bottom so that by the time it gets to the top, it will have slowed down and be still going at least this fast by the time it gets to the top. So can we determine the minimum speed it must have here at the bottom in order to still be going at least that fast at the top? That's our job. And the work energy theorem is a perfect tool for answering that question. So we state our work energy theorem. And for our net work, as we go from the bottom to the top along that arc, the net work can be found by summing up the works done by each of the forces. That's why we did this here. Work done by tension was 0. Work done by gravity was minus 2 mgr. So 0 minus 2 mgr equals our change in kinetic energy, which equals the kinetic energy at the top minus the kinetic energy at the bottom. So we write negative 2 mgr equals 1/2 m v top squared minus 1/2 m v bottom squared. And so we want the top speed to be this. We want the mass to be going at least that speed at the top, so sub in root gr for v top, minus 2 mgr equals 1/2 m v top squared, so square root of gr squared gives us gr minus 1/2 m v bottom squared. Okay, I see that I've got an mass and a 1/2 that I could factor out from the right-hand side. I'll factor out the 1/2 m, leaving a gr minus v bottom squared. equals negative 2 mgr. At that point, I'll cancel out the masses on both sides, divide through by mass. I'll multiply both sides by that 2, and we'll get negative 4 gr equals gr minus v bottom squared. Finish the algebra. V at the bottom will equal the square root of 5 gr. That's what we're looking for. Therefore, our conclusion is that if the speed at the bottom is less than the square root of 5 gr, the mass will not complete the loop successfully. The mass will not complete the loop successfully. The string will go slack and the mass will fall off the circular path before it gets to the top. And then it will become, if there's no longer tension acting on it, because the string went slack, then gravity is the only force acting on it, and a force, an object subject only to gravity, we say is in a state of free fall. So the path will become parabolic instead of circular if we're not going at least that fast at the bottom. Okay, so just as this result here, I recommend memorizing for quick use and being able to rederive. This is also handy to have memorized and to be able to rederive using this energy argument. So I hope you see how the tools of dynamics and kinematics and the tools of work and energy are complementary to each other. Dynamics can tell us something like this, but it required an application of energy to tell us this.